And we're back with another PicoCTF challenge. This time, what lies within a forensics challenge. Description: there's something in the building. Can you retrieve the flag? And then as a hint, we get there's data encoded somewhere. There might be an online decoder. So let's go ahead and let's download this. Looks to be an image, buildings.png. And if we open it up and we take a look, looks like a normal enough image. So let's go ahead and let's start by taking a look and seeing if we can't find out something about the metadata. So we'll use EXIF tool on buildings.png and we'll take a look at what we see. And we don't get much here, nothing really of interest. So let's try strings, and we'll require that it be at least the size that a typical flag would be. So let's say at least 9 characters. And we get a bunch of matches, a bunch of potential candidates, but they're all pretty short. You know, it has to be PicoCTF and the curlies, and the only things that seem like they might reasonably be long enough, they're not that interesting. They don't change that often. It doesn't seem like it could possibly encode the information. So let's move on. There was a hint that there might be an online tool. So I Googled PNG online decoder, and the first result was this Steganography online link. And I tried decoding, and we see it shows the input image. And when we hit decode, we get a flag. Let's try this guy out. And that was it. But I think the spirit of the CTF is about learning. And if all you learned was to Google and then dump it into this online decoder, really you haven't learned much. So let's learn something. We'll look for documentation on this, and we can find that this guy has this GitHub repository here, and there's a script.js, which seems to be doing all the work, and he has a description in his README, and it says that he'd wanted to look at steganography for some time. This is a small project he made. It provides the functionality to encode a message in an image and to decode the message from the image. Steganography is the art of hiding a message inside another message. It's not a means of cryptography, although you could first encrypt the message and then you could put it into the image. And then we get into implementation details. I'm going to read this, but don't worry. I have pictures. We're going to talk it through, and it's going to make a lot of sense at the end. Implementation details. The user chooses an image. The image data is then normalized, meaning that each RGB value is decremented by 1 if it is not even. This is done for every pixel in the image. Next, the image is converted, the message is converted, so that's our secret message, to a binary representation, 8 bits per character of the message. So it's going to be an ASCII encoding. This binary representation is then applied to the normalized image, 3 bits per pixel. This concludes that the maximal length of the image, of the message hidden in the image is, and then we have a formula here. So let's break this down. Image width times height, that's the number of total pixels that we have, right? And then we said that we can store 3 elements or 3 pieces of our secret message per pixel. And it takes 8 bits to store 1 letter of our secret message. So this gives us a sense of how many total characters of our secret message we could store given an image. And then you write your secret message in using the least significant bit is what this is saying here. And then you can, of course, read it back out. So let's break this down quickly. So the steps that we just had described were 1, what's the message? And in this case, let's use the example of a capital A is our secret message, which in ASCII is represented as a 65, and in binary, that is this value here. Second, we're asked, what's the image that we want to hide it in? And we need to understand a little bit about images. So let's go over to GIMP. GIMP is, think of it like Paint, MS Paint on steroids. I have the image that we're submitting right here. And if we zoom all the way in, really close, what you can see is individual pixels. And it's harder in some areas to see. Hopefully it shows up well here. If you look in this bottom lower corner, you're going to see the coordinates. So this is position 2, 8, so meaning 2 on the X and 8 on the Y. If we move over to the next block, it's 3, 8, move down, becomes 3, 9, 10, 11. So every image is just a series of these individual pixels that are very small that have a color. And that color can be represented in a number of ways. I'm going to take the dropper and we're going to look over here. So the dropper, sorry about that, had a minor hiccup and originally things didn't capture the windows. So here we can see there are many ways you can represent colors inside of a computer. The way that makes the most sense to me, just because I'm an engineer, I'm not an artist, I don't know what all these fancy words are, is just simple red, green, and blue. You combine those three and you can make any color. So that's what you see on the top. You're also going to see H, S, and V. So hue, saturation, and I don't know, value, I guess. I don't know what those are. They don't make sense to me. I'm sure they have a good reason for existing. But what I want to show you is how we can make any color by pulling along something like green. So you can see the resultant color is shifting to red, it's shifting to purple, orange. Same thing with if we pull the red slider, we can see we start changing the values. Again, don't worry too much about these bottom ones. Just worry about this set of 3 at the top. You'll see these don't move because they're independent of each other. The HSV, yeah, I don't know. Again, I'm not a fancy artist guy. So if we wanted to make something like pure white, we would slide all the sliders out to their maximum value of, it's kind of weird. There we go, of 255. I guess if you exceed that, you end up in red. So what's happening is we're going to do something called least significant bit encoding. And what that means is we are going to just change this ever so slightly. So rather than it being 84, we'll make it, say, 85. Now that moved. This is not the same color. Did you notice it move? I think it's incredibly hard to tell. And each of these values will be tweaked at most one position. So each pixel you can think of as RGB, and one additional element which is called alpha or opacity. And I'm going to add over here another layer, so we're going to be compositing. So I've added a layer that was that solid color that I selected, and you can see it's on top of our image. If we change the order, so think of this like stacking paper on top of each other. If we change the order, then all of a sudden our picture is on top. Now our picture is underneath the solid color. If we were to change the alpha, we'd be able to see through this layer. So there's 50% opacity. And as we go lower and lower, less of that top layer shows. Okay, this is all going to make sense now. And I'm going to bring this together when we go back to our slide. So as we established, this image is just a series of pixels, which we can represent as red, green, blue, and an alpha channel. The values go from 0 to 255, and we see these values are represented here as just binary. Don't worry too much about the values. I just picked random values. So the alpha is 255. All the ones are there that can be there, and these other values are smaller values. And obviously we have way more than just the 3 pixels. I'm just doing 3 because I'm not going to do a million like this would have. So we're going to normalize it, was one of the steps that the description told us about. And the normalizing just involves making everything an even number. And in binary, that's really, really easy because any binary number that ends in a 1 is going to be odd. So we'll just quickly perform this. For the R, G, and B, we're leaving alpha alone because that wasn't mentioned in the description. So now we've normalized it, and we're going to encode our message. And this is our message. So we'll start with a 1 in this position. And we need a 0, which we have, a 0, another 0, another 0. I'm just working my way along this guy. Yet another 0. I've lost count almost at this point, but I think it's this guy needs to become a 1. So now we've encoded our message across these 8 elements. So 1, 0, 0, 0, 0, 0, 0, 1. And now we have a new image, which has been slightly tweaked. So now that we've walked through and kind of explained how this should work, let's actually go and let's try encoding an image. And this is actually really nice. When you look at this, you're going to see this is unobfuscated JavaScript. So we can read the code right in here. And as we look at things, we can see there's an encode message function. And there's also a decode at the bottom. And so we think we know how this works. And what we're going to do is we're going to run through this step by step, and we're going to see if it actually does what it says. So let's choose to encode in our buildings.png the message, please subscribe. So there's our original image right there. We hit our breakpoint, and some of this stuff you don't really need to know about. You know, when you have nice, well-documented code that you can read, it's okay to skip over some things. We seem to be establishing, you know, some different elements on the page. So like a binary image we're hiding, and an error image. We're grabbing some things. If we were really curious about this, we could learn more by coming out here and seeing that now original context is declared as a canvas rendering context 2D. What is that? Well, we could look up the API specification here, and we could read on Mozilla, and we could learn all about it if we really needed to. But fortunately, this is probably going to be good enough since we can interact with it and we can debug. So we can see things like we're getting the width and the height. We're doing a check. Remember that formula we talked about where we have to make sure that we can keep our message, our please subscribe, a secret in this image. Is there enough space? So that's the calculation that's being performed here. Now we're setting up new canvas items. We're not really too interested in that. But normalization, this is what we talked about where we set everything to be even. And so let's make sure this works and makes sense. We have a pixel array, and so it's just a large series of numbers that fit that format that we were talking about, where for each pixel there are 4 values, a red, green, a blue, and an alpha channel. So 0 to 3 is a pixel, then 4 to 7 is another pixel, and you can see the alpha is always 255. So there's no opacity to this. And what we're going to see is we are looping over our pixels. So our array of pixels, we loop over it, and we're going in groups of 4, like we discussed, because you have those 4 elements for each pixel. And then we're going to run through R, G, and B, and if the pixel value that is the R, G, or B for that happens to be even, then it's fine. If it's odd, we need to fix it. So I'm going to just set, oh, I already had set it over here. I'm setting a watch so we can see what this value is that we're going to be looking at as we get it. And we'll step over, and we can see it's the 34, which is the red value. 34 when we apply the modulo operator, so that's also known as the remainder operator. That tells you what the remainder of division by 2 is. And division by 2 is going to give you 0 as the remainder. So it's not 0. So we don't have to do anything. We don't have to fix that value. Next one, though, is 35. 35 will have a remainder of 1 when we divide by 2 because it's an odd number. So you can see what we're going to do is we're going to subtract 1 from it, and it should become 34. All right, so this works exactly as we expected. We get down here, we have this helpful message that tells us we convert the message to a binary string, and we'll just walk through one quick example of what's going on. We have the message, we're going through each element of the message. So we're starting with P here, and we're going to turn it to binary. We're going to pad it out, as it says, if need be. So if it was like binary 1, we would want it to fit in the slot that we have. We want byte-sized chunks, so 8 per each. I'm not going to dwell on this too long, but that's what a P is, and we're just adding this on to our binary message. We can see we're going to build that up. At the end, we're going to have a lot of binary, which we do. And then finally, we're going to draw in the image, and this should look very similar. We're doing a for loop where we're writing to each pixel, and we're going to write, we're going to add to R, G, or B, depending on where we are in the binary message. Sorry, that's moving. That's very, very annoying, I'm sure, for you guys too. So right now we're looking at the first pixel's R value, and our message to encode is binary message. We're on position, the first position, 0. And so we don't need to encode anything. So it will remain the same. The next one, though, we're going to see this change because we need to encode this 1. And I think you guys get the point at this point. So let's go ahead and let's let this all run all the way through. And what we can see, we had an original image. We have a normalized image where everything has been slightly changed. And then we hid the image in the building PNG. And just to verify that the decoding works, it looks very similar, but we'll call this our building. And we will try the same thing for the decoding. We're going to choose our building. I'm going to make sure I have a breakpoint set. I do, and we're going to decode it. And a lot of this is going to look very similar. I'm not going to bore you guys too much more with this, but we're just reading off all the RGBs, their least significant bit. So we've got each pixel here. We read RGB, and we build up a binary message. So let's go ahead and let's run to that point. And we can see we've recovered our binary message. Now we just need to change it from binary back to ASCII so we can read it. And then we're going to write to the screen. And beautiful. Please subscribe. Anyway, I know this is a little longer as I walk through the whole problem, and maybe I've already lost everybody as you guys all just said, hey, I already got the flag. But I think it's useful to go through this and to see how easy it can be to do your own steganography. This was not complicated code. This was very straightforward. It's good stuff. Thanks for watching the video. I'm going to keep making these, and you can help in a number of ways. First, liking and subscribing encourages me to continue doing this type of content. It sounds like BS, but seeing people say I helped them does make my day. Second, in the comments or on a subreddit I made, you can suggest future content. Every 2 weeks, I'll look at what the most requested challenge is and make a video on it. Finally, I have a Patreon if you'd like to financially support this. Thanks, and have a good one.